Okay. Hey guys, so today we're going to be going over free fall and gravity. We just went over acceleration last class, and so today we're going to be looking at a particular type of acceleration and the impact of that acceleration, and that's gravity. Okay, so let's start with our essential questions for today. Number one, what is gravity and what unit is used and why does that unit make sense? Number two, what are weight and mass and how are they similar and different? How are they related? And number three, what is a Newton and why does this unit make sense? So units are going to be a big part of what we're doing in this first unit. Remember, these are the derived units we've been talking about, and we need to think about them in terms of the base units that construct them, and that can help us understand the mathematical relationship that creates them. Remember, math equations represent relationships between the pieces of the puzzle. All right, so let's jump right in. Now, first things first, this is a big ask, I understand that, but imagine there is no air resistance. In physics, we have to make some assumptions every so often to help us simplify the math. If you were doing this as a professional up at the upper college level or even as a job, you wouldn't be able to do this. If you're starting to look at the landing of an airplane, you can't neglect air resistance. If you're starting to look at the influence of air on a flying football, you can't neglect air resistance. But for most of the calculations that we're going to be doing, we're going to assume air resistance is negligible. It's at least small enough to not impact our calculations very much. Okay? Now, an object moving under the influence of only gravitational force is said to be in free fall. And when that is the case, the acceleration of that object in free fall is 9.8 meters per second squared. Now, those units should look familiar. That's what we talked about in terms of acceleration. But this is only true if you neglect air resistance. When we start thinking about this, a common example that we utilize is one of the experiments done by Galileo. Now, Galileo dropped a feather and a hammer to the earth. Now, when you do this, which one is going to go ahead and reach the ground first? Is it the hammer or the feather? Now, you probably were able to come up with the fact that it's the feather. And this is what we would see time and time again on Earth, but that's because of air resistance. And we'll talk about that a little bit more next week as we finish up this unit before we go ahead and take our next exam. So, is that same statement true in a vacuum? Remember, a vacuum removes the air resistance. And there is an amazing video that goes ahead and takes a look at exactly this with Brian Cox. And I would encourage you to go ahead and look at this multiple times if you have time for it. There is an ed puzzle that I'm throwing in there for you so that you can go ahead and watch through this and you'll go ahead and get a grade for it. But it's an awesome video. And unfortunately, some of the depths that he starts to go to at the end of the video are more than we're going to have time for here. But he starts hinting at the impact of different forms of relativity and what that does in terms of Einstein's view of the universe. Okay, so I encourage you to go ahead and take a moment out of your notes, go do the ed puzzle, and then come back and finish. All right, we'll see you back here in a little bit. Welcome back. Okay, so now let's go ahead and move on and start looking at gravity. What exactly is gravity? Now, gravity is the attractive force of one object on another object. And as we get further along, we'll go ahead and look at Newtonian gravitation and actually come up with a really kind of cool equation that's going to help you calculate this between two bodies. But for what we're doing in this unit and what we're learning in these basic things, we're going to go ahead and just use the acceleration of gravity on Earth as 9.8 meters per second squared. Now, remember, that's on Earth. If you go to the moon, you go to Jupiter, that's not going to be the same acceleration. Gravity exists everywhere that matter does because all matter attracts all other matter, which creates a gravitational force. The strength of that gravitational force between the objects is dependent on two main things. One, the masses of the objects, The bigger the object, the more gravity it's going to exert. And two, the distance between those two objects. The closer they are together, the greater the gravitational force between them. Now, let's try a really quick thought experiment. When you go ahead in your room, take a minute, pause the video, and I want you to go ahead and jump up and then kind of observe what happens. Now, I know you can predict what's going to happen, and that's that you come back down. When you are up in the air, where is the greater force? Is it the force on you or the force on the earth? So I want you to think about that as you go ahead and do that. Okay, pause the video here and go ahead and give that quick experiment a try. Okay, so which one is it? On you or on the earth? Most of you probably are going to go ahead and say that there's a greater force on you, but in fact, it's a little bit of a trick question because the force is the same. The gravitational force between any two objects is the same on both those objects. But it turns out that you're much easier to move because you have less mass than the Earth is, which takes far more work. And so most of that work is done on you rather than on the Earth. But the Earth still has that same amount of work done on it. You just, because it's more massive, see less acceleration. All right. Now, most objects in the universe are just too small to have any noticeable gravitational effect on any other object. We can think about things like atoms, even you, me, your friends. So next time you're walking down the hall, we take one of these guys out and you say, you know, I want you guys to go ahead and walk up to the girl that you've been so interested in. I want you to say, I know you're attracted to me. Right? Now, you may think that's kind of a weird thing to say, but it's the law of gravity. All objects are attracted to each other. So it may be a weak force, but all objects are attracted to each other. So you can always use that as your pickup line. Okay. The two biggest gravitational forces that we notice, however, here on our planet are one, the sun. It is the most massive object in our solar gram. You can see that 1.98892 times 10 to the 30th kilograms is huge. And it makes up about 99% of the mass of the entire solar system. This exerts a huge gravitational force, and that's why all the planets stay in orbit around the sun. The second one is the Earth, partially because we are on it, so our proximity, our distance is really close together. It's decent sized as far as rocky planets go, but in terms of planets overall, it's pretty small. Okay, it's not nearly as big as the gas giants are. And so we're looking at 5.9724 times 10 to the 24th. That's a magnitude of 10 to the 6th smaller than the sun. But it's massive enough that the gravitational force keeps us from falling off the planet and keeps the moon in orbit around it. But remember, we are a pretty small planet. If you go ahead and take a quick look at this, right? If we take a look here, Mercury, Venus, Earth. This is the one right here that's us. That's the third rock from the sun. Then you get Mars, but then take a look at how much bigger these gas giants are. You can go ahead and exclude little Pluto out here. But this is more of a Kuiper Belt object and less a planet in the traditional sense, which is why it's been demoted to a dwarf planet. Now, when we take a look at gravity in space, we see astronauts floating around, and we use the term very commonly weightless. It's actually not true. It's not a good representation of what's happening. They're not weightless, they're just in free fall because the planet is got such a strong gravitational pull that the spaceship, the moon, all these other things are being pulled around it, but because of their momentum, they're going straight too. So essentially, it's at a point in orbit where it's in constant free fall. Okay. They are not close enough to the gravitational force to have it be strong enough to pull them down, whereas if they got closer to the Earth, they might be. The moon has gravitational pull, but because it's so small, it's not really doing as much pulling in the sense that we're thinking. Now, this is what we call an inverse square law. As you leave the distance that you go away from the surface of the planet, actually from the core of the planet, the rate at which the gravitational force drops off is measured in 1 over d squared. So it's a parabolic decline in terms of the strength of the force. So as you increase distance, force declines at an inverse square. This is important, and this will come back when we look at Newtonian gravity, and we'll look at this once again when we start looking at electricity next term. Okay, so important thing to understand. We'll go ahead and come back to it. Uh, the next thing I want to highlight here is that weight and mass are often used synonymously, but they're not the same thing. Okay, it's important. This is probably one of the most important things to kind of keep in mind. Mass is how much matter an object contains, whereas weight is the force of gravity on that object's mass. Okay, mass never changes, whether you're here on the moon, whether you're on Jupiter. Okay, you have the same mass, but your weight changes depending on the gravitational pull. If you take a 200-gram mass to the moon, it still has a 200-gram mass. If you put it in outer space, it still has a 200-gram mass. The gravity changes in terms of its weight because of the force of gravity being different, but the mass does not change. So the weight will change whenever the amount of gravitational force changes. As a 200-gram mass will weigh less on the moon than it does here on Earth. It's about 1/6. Okay? So the force of gravity on an object is called its weight. Now, most of us are used to measuring our weight in pounds, but this is not actually the SI unit that we use. At Earth's surface, gravity exerts a force of 9.8 newtons on every kilogram of mass. Okay? So when we start looking at this, if you have a 1 kilogram box, it weighs 9.8 newtons. If you have a 2 kilogram box, it's 19.6 newtons. 3 kilogram box, 29.4 newtons, and so on and so forth. But the big takeaway here is to make sure that you remember that weight and mass are not the same. Mass is a fundamental property of matter, and we measure that in kilograms. Weight is a force measurement, and that's measured in newtons. Weight changes depending on the mass and the gravity upon that mass. So if we go ahead and measure the mass of a rock, okay, we can see that it's 10 kilograms, and on Earth, that will weigh 98 newtons. You take that same rock, its matter hasn't changed, it's just now in space on the moon, and instead of weighing 98 newtons, it now weighs 16 newtons. Okay? Because there is less gravitational pull or force on that rock because the moon is so much smaller than the Earth is. So how do we do these calculations? Well, we're going to cover this more as we go ahead and get into our next unit and we start looking at mechanics in more detail, especially at forces and free body diagrams, etc. But the basic equation is this: weight equals mass times gravity. Now, gravity, remember we said earlier in today's notes, is actually a type of acceleration. And weight then is actually a force. All right. So if we go ahead and take a look at this, weight, remember we just said, woo. Hold on. Let me see if I can correct that. Okay. Weight is a force and gravity is an acceleration. So we could actually write this as xf equals ma. And this is actually Newton's second law. So if you remember from physical science days, F equals ma, and this is one of your basics, where F equals force, m equals mass, and a equals acceleration. Now, for all the calculations we can do here on Earth, we can go ahead and use an acceleration of g. So a equals g, which equals 9.8 meters per second squared. And those are our standard units that we start looking at when we go ahead and take a look at accelerations. All right, so let's go ahead at this point and move on, but you should be able to use your algebra skills to go ahead and manipulate this equation to solve for any of the variables, whether it's weight or mass or gravity. Okay? And this is a valuable thing to understand. So weight, remember, is a force. And what's the unit that we use for force? Right, it's a Newton. Okay, don't get confused with the pounds, but this should give you an idea of what a Newton is. So if we use the gravitational constant of g, 9.8 meters per second squared, and Newton's second law, we can actually go ahead and find out the unit of a Newton. So mass, remember, is a unit that's going to be measured in kilograms. Okay, so mass in kilograms. And an acceleration, we said the standard is going to be meters per second squared. We're timesing these together. So force is going to be measured in the units of kilogram meter per second squared. That is the standard unit for force, and we have a name for that. So a Newton, 1 Newton, is equal to a kilogram meter per second squared. That is a derived unit. Okay, kilogram is a base unit, meter is a base unit, seconds is a base unit. We combine these, and that tells us the relationship that we have here. Force equals mass times acceleration. And if you remember, if you wanted to take this back even further to see where the meters per second squared came from, remember that acceleration is equal to delta V over delta T. So this is equal to VF minus VI over T final minus T, oops, that's supposed to be a T initial. And since we usually just do this as time as a T, you can see that when we go ahead and do this, velocity actually can be broken down even further. Velocity is distance per time final minus distance per time initial over time final minus time initial. So you can see how it can get a little complicated if you break it down to its simplest roots, but ultimately that's where the units come from. A Newton is force equals mass times acceleration. Mass, the SI unit is kilogram. Acceleration, the SI units are meters per second squared, which is a derived unit that comes from over here, delta V over delta T. Okay. All right. So let's clear these drawings and go ahead and move on. And you should know, because of the math that we just did, that force is a quantity measured in a standard metric unit known as a Newton. Now, a Newton is abbreviated by an N, a capital N. And so to say 10 newtons means 10 newtons of force. And we'll talk more about this idea of forces when we go ahead and get into our next unit. But when we go ahead and look at this, 1 Newton is the amount of forces required to give a 1 kilogram mass an acceleration of 1 meter per second squared. So a Newton is equal to 1 kilogram meter per second squared. Now, if you want to compare this to pounds, which is what you went ahead and did before, that's what you weigh yourself on, 1 pound of force is equal to 4.44822162 newtons. Okay. So if you think about what you weigh on a scale, if you want to convert that into newtons, you can times it by the conversion factor you see right there. Okay. All right. That's all we have for the notes. And so we'll go ahead and leave you there. Thank you so much, guys.